Greetings and welcome, friends. We're taking a look at 4.1 from the Big Ideas Geometry book. We are covering a new chapter about transformations, and today specifically we'll be talking about sliding a point or an object in a distance and direction, which we'll refer to as translations. But before we even get there, we get to talk about this idea of vectors. Okay, and a vector has got two components to it, I guess. It's a quantity that has both direction, all right, and magnitude. So two pieces going into that. Magnitude would be its length or something to that effect, and is represented in the coordinate plane by an arrow drawn from one point to the other. So here's vector PQ, for instance, and vector PQ, you'll notice, is almost like a ray, except it's kind of got this harpoon of an arrow on it. It's a one-sided arrow. So the diagram shows a vector. The initial point or starting point is P, like so. And the terminal point or ending point is Q, right there. And the vector is named vector PQ, right, which is read as such. The horizontal component. Now, here's an interesting idea. So my vector has a direction and distance, or magnitude, but vectors are most frequently, their direction is given as a horizontal and vertical movement. That I think of those as two separate components, and yes, this would be a right triangle here. So I could have thought of it as an angle with some sort of degree measure, but for vectors, we actually think about these as moving left, right, and then up, down as we move by those components. So the horizontal component for PQ is 5 units to the right. The vertical component is 3 units up. And whether I did vertical and then horizontal, or horizontal and then vertical, it actually won't matter either way. Notice it ends up at exactly the same point regardless. So that's what we'd end up having. Let's see, the component form of a vector combines the horizontal and vertical components, and it's written almost as an ordered pair, except notice these are kind of large. Are those angle brackets? I think is what we call those. I don't remember. But yeah, it's not a curly brace. It's not a square bracket. I think angle brackets is what I'll call them. So so there's our vector. The first component given is the vertical, and the second, or sorry, horizontal, and the second one is the vertical. So we can use vectors to describe motion. Vectors are something that are often represented or used to represent movement in physics or forces in physics. So this type of mathematics is frequently used in the world of science, but we're going to use it for translations today. And let's see, I've got a little sketch here for us, like so. And they're asking us, so let's see, example 1, in the diagram, name the vector and write its component form. So the vector is going to be, in this case, J to K. And remember, it's just a half arrow. It's the little harpoon arrow. If I wanted the component form, well, I've got to actually ask the question, what is the horizontal component? What does this appear to be moving by horizontally? Looks like it's horizontally moving by 3 and vertically moving by up 4, which, by the way, those components can be given as negative values as well. So a negative horizontal would be to the left, and negative vertical would be down. So the component form would have been 3, 4, referring to the vector that moves in that direction and that distance. Does anyone know what this distance would be in this case? What that magnitude would be? Well, since this is a right triangle, we could use Pythagorean theorem. I believe this is just going to be a 3, 4, 5 Pythagorean triple, which, by the way, not that your book covers this, but I'll tell you this much. If I wanted to know the magnitude of a vector, if I wanted to refer just to that distance, they actually use these absolute value bars, and I would say that the magnitude of the vector is 5. But you don't have to know that, so you can erase that from your memory. I'm sorry I ever distracted you. Right? You can learn that elsewhere, friends. So let's see. Let's talk about transformations. All right, you guys got this information down. So a transformation is a function that moves or changes a figure in some way to produce a new figure called an image. And we kind of worked with those ideas in Geometer Sketchpad moments ago. Another name for the original figure is the pre-image, right? That prefix pre, you can tell that was where we started. This is where we ended. I guess they could have decided with image and post-image, but this is what they've committed to as mathematicians. So let's see, the points on the pre-image are the inputs for the transformation, and the points on the image are the outputs. Okay, so transformations can be all sorts of things. We'll cover a variety of them in this chapter, but today we're talking specifically about translations. So translations. Your image is not going to be in color and won't make as much sense, but here we go. A translation moves every point of a figure the same distance in the same direction, so kind of move it by a vector. More specifically, a translation maps or moves the points P and Q of a plane figure along vector AB. So if it's moving by vector AB, notice that vector AB, all of these points are being mapped A units to the right and B units up, like so, which can also be found by taking the pre-image coordinates and adding A to the X coordinate and B to the Y coordinate, and that's how you can find those values. All right, so my image, the P prime, will be just adding the vector's horizontal and vertical components to the horizontal and vertical coordinates of my original point. And notice one of the easy ways to do a translation is to look at just the endpoints of all your segments and then just connect them. And I think we can safely assume that all of the infinitely many points here got mapped to their appropriate image along that blue segment up there. All right, so let's see. And let's see. Yeah, let's see. All right, I'm trying to figure out what I've already said. Here we go. So the translation maps or moves points P and Q of a plane figure among vector AB to the points P prime and Q prime, so that one of the following statements is true. Interesting. One of. So P prime is equal to Q prime. All right, that's talking about those vector distances. Notice the congruence here. And P prime is parallel to Q prime. So notice those were also denoted there. Or P prime is equal to Q prime, which is what we had, and P prime and Q prime are collinear. So that would have been if we were mapping two of the same point by the looks of things onto itself. If they were, or actually, no, because if the points that I was moving were being moved by a vector that happened to be in the same direction as those points. So let's say this orange segment, or ray rather, is my vector. The image for P would have landed here, and Q moving that same distance would have landed over here for Q prime and P prime. So they're saying like that these vectors could have been collinear rather than parallel if they happen to be on top of each other. So interesting, very specific to that distinction. You won't see that happen that often. So let's see. Let's do example 2. You guys have a little coordinate plane for this example already given to you. Translating a figure using a vector. And let's see. Let me get my coordinate plane up here. Like so. So you got this, Malik, you're following along. It says the vertices rather of triangle ABC are 0, 3, 2, 4, and 1, 0. Translate triangle ABC using the vector 5, negative 1. All right, so I've got to kind of like plan out where my coordinates are going to be in order for me to fit this. So let's see, my smallest x coordinate is 0. My largest one was 2. I'm adding 5 to it. So I think my y-axis should be somewhere over here. Let me, where'd my ruler tool go? Not selecting it. There we go. So I think I can work over here for my y-axis. Just kind of make this a little bit bolder there. So this will be my y-axis, and let's see, for my x-axis, what's my smallest y coordinate? Looks like 3, 4, and 0, and I'm moving them all down by 1. So so I think I can draw this kind of about there for my x-axis. Just trying to make appropriate space. Oh, never had that problem before. Make appropriate space for this. Somewhere about there should work. So that way I'm kind of zoomed in on the more interesting values. Like so. So this will be my x-axis. So let's plot my original. I'll use green for my original point. So triangle ABC, 0, 3. Starting at the origin, don't move left or right, move up 3. There's point A. We might as well label it. B is 2, 4. So right 2 and up 4. There's B. And C is 1, 0. So over 1 from the origin, don't move up or down. There is C. We could also connect those dots. I guess they did say it's a triangle, didn't they? All right, let's see. You guys can grab rulers from the front of the classroom if you want to use a straight edge. And let's see, I've got my nice little, yeah, you're using multiple colors too. What a good idea. All right, so there's triangle ABC. We're moving this by vector 5, -1. Okay, so the vector 5, -1 is telling us to move horizontally by 5 and vertically by 1. Let's see, so let me get a roughly horizontal line here. Nope. 0 degrees, roughly. All right, let's map point A. So if I move 5 points, 1, 2, 3, 4, 5, landing about there, and then down 1. Let's see, something like this. What? Our homework is going to be like this. Yes. Graphing a bunch of stuff. Or answering questions regarding vocabulary. So let's see. So A prime will be right 5 and down 1. There is A prime. Something like, actually, maybe I'll label it on. Yeah, it's not that bad. B prime, let's move that by over 5. 1, 2, 3, 4, 5, and down 1. There's B prime. And C prime, once again, over 5. 1, 2, 3, 4, 5, and down 1. There is C prime. And let's draw our little triangle. Why not, shall we? Oh, it doesn't let me have my points too close to each other. Something like that, and something like that. And here is here's the image. Yeah, it's not that bad, right? I mean, there's like some new ways of writing things, some new notation. But yeah, that's the basic idea. Have a quiz on this tomorrow rather than our test. So guys, if I want to talk about the function, the translation that did this, for any point x comma y, you could view this as having become x plus 5 comma y minus 1. All right, so all of my points got mapped to new points where I was just simply adding 5 to the x coordinates and subtracting y to the subtracting 1 from the y coordinates. So right, so nothing too crazy. Nothing too crazy at all. Let's see. I'm so glad we don't have to redraw this next example from scratch. Here we go. Example 3. Is write a rule for the translation, right, ladies and gentlemen, of triangle ABC to triangle A prime, B prime, C prime. Okay, this time, oh, it's actually moving backwards, ish, if you want to think about it like that. It looks like it's actually from A to A prime. Yeah, it's going left 4 and up 1. So my vector would have been, yeah, exactly, Malik, -4 comma +1 is my vector, which is perfectly fine. Perfectly fine. We can move in that direction. But they're asking for a rule for the translation. This is the rule. For any point x comma y, that then became a new point, which was x minus 4 comma y plus 1. So if I asked regarding the rule for translation, that's what I'm referring to, something like that. All right, and every point got moved exactly the same amount in exactly the same direction. All right, that's not that bad. Now, what do you guys suspect about those triangles? Do you think those have the same angles and the same segments? What do we call sketches that are exactly the same size and shape? Congruent. Congruent. Right, yeah, good word, good word. All right, example 4. Translating a figure in the coordinate plane. Graph quadrilateral abacus with the vertices as given. Let's see. Am I going to have enough space for this? Let me think. All right. Let's see. All right. All right. Am I going to have enough time, actually? Yeah, I think, tell you what, guys, this is going to be the super shortcut version for this problem because we're running out of time. Watch how amazing my graph is. Wow, look at those skills. Look at those skills. So let's talk about how I would have done this, right? Plotting A would have been left 1 up 2, B would have been left 1 up 5, C was over 4 up 6 from the origin, and D was over 4 up 2. And now let's see, it says translate it by the value plus 3 minus 1. So that's kind of like if I was doing the vector 3 comma negative 1. And notice that for any one of these points, if I go right 3 and down 1, or I could have thought of it as down 1 and right 3, I will land at its corresponding image. Nothing too crazy there, right? Nothing too crazy. And so yeah, so that's not that bad. Now the fact that my image and pre-image are congruent after the transformation took place, we actually have a special word for that. Let's see. We call that rigid motion. Is a transformation that preserves length and angle measure. Another name for a rigid motion is an isometry. A rigid motion maps lines to lines, rays to rays, and segments to segments. And everything that happens here will result in congruent angles to our original angles and congruent sides to our original sides. And here's a postulate, something that we should accept as true without proof, the idea that a translation is a rigid motion. If all I'm doing is moving the object, I'm not stretching it or smushing it or turning it, I think you would agree that it's going to be the same size and shape. I don't think that's that hard to believe. All right, and just to be abundantly clear, okay, if I'm doing a translation, that my original segment DE would be congruent to D prime D prime. EF would be congruent to E prime F prime. That all of the corresponding, notice this word, corresponding. All right, this is going to come to play later on in this course. Corresponding sides are congruent and corresponding angles are congruent, right? You're welcome for my not making you write all that down. All right, and here's a picture of that. All right, that after a translation, notice that, right, this angle is congruent to that, this side is congruent to that, this angle is congruent to that, etc. That because it's a rigid motion, all of the corresponding parts are congruent. All right, super helpful language right there. Let's talk about, it turns out I can do multiple transformations one after the other. And this is going to be called composition of transformations. All right. And check this out. The composition theorem says that the composition of two or more rigid motions is a rigid motion. Okay, so watch this. If I take this and I translate it over to this one, and I take that and I translate it over to that one, because translations themselves are rigid motions, the combined effect of both of those translations will also be rigid. Okay, so it's almost like transitive property of rigid motion? Maybe, kind of, right? Like, yeah, I think it makes sense that if this to that was rigid and that to that was rigid, then this to the end result would have been a rigid motion. Okay, so performing a composition. Ah! It's okay. All right, let's see. We're still moving here. Example 5, are we going to make it? We might not get to example 6, but we will get through example 5. It'll be a-okay. So guys, here we go. Example 5. Here we have multiple translations occurring to the same sketch. Okay? What do I know about my beginning and my end results? They're gonna be congruent to each other. Okay? So here we go. All right, for sake of time, I'm gonna make this my x-axis. Kind of sad. No. Yeah, it's so ugly, I know. There we go. There's my y-axis. Let's plot these points real quick. So r is -8, 5. So -8 and up 1, 2, 3, 4, 5. Right there is r. And s is at -6, 8. So 1, 2, 3, 4, 5, 6. And up 8 is right there is s. So rs is something like that, like so. And I want to translate both of these things. So the first thing I'm going to do is add 5 and subtract 2. So move it 5 to the right, 1, 2, 3, 4, 5, and down 2. So this would be s prime. And 5 to the right, 1, 2, 3, 4, 5, and down 2. Here's r prime. So there's my first transformation. It's rigid. And now I'm going to do another translation. We'll use blue, I guess. So from r prime, go left 4, 1, 2, 3, 4, and down 2, 1, 2. So here's r double prime, right? And let's see, for the y, yep, for s prime, sorry, left 4, 1, 2, 3, 4, and down 2. Here is s double prime. And the end result is going to be congruent and in the same right location. It's a rigid transformation as my starting value. All right, I think we're just about out of time. So thank you for watching, Internet friends. Have a good day.